Now let's have some future look at some future developments. It's like complex timber structures. It's nothing new, actually. There's a little bit a revival. Already 30 years ago or more, 1883, big domes, 160 meters span were built. So this is a very easy situation. There are some books where you can actually do design on that by hand. They already managed to do some prefabrication, cantilever, erection process for these solutions. Or this structure here, which is a recycling hall that has been built by Julius Natter in 81. This member here is about 90 meters long, came in 3 parts, connected in 2 splices. This was for a recycling factory, very special environment in terms of for building physics and so on, durability. But these were fairly simple structures because there were no big openings and so on. But the interesting thing, and why I'm showing that is, at that time, there were no computer models around. You would rely on the competence of the carpenters, of the engineer, or in finding the good solutions. And actually, to do the design, you just relied on some very simple models. But and this was also the start, actually, when first modeling tools arrived or came onto the market to do some design for the engineer. At that time, 86, they were even capable to do double curved members. To design these things, having very complex structures here, no idea how they did that. Probably some poor fellows had to work day and night and do some hand calculation. They had some basic tools already starting and giving some aid to the people. But quite interesting actually to look back and see that the state of the art, Europe and in other places was very good at that time. Maybe interestingly also is these structures are mainly engineered structures. You had to mainly deal with statics, with forces, with design, maybe some fire issues, maybe some durability issues. But the main topic was to have this engineered structure done. So it was quite straightforward, if you like. What do we have today? We have heaps of standards. In Switzerland, we would design according to a Swiss standard or Eurocodes, whatever is more appropriate. We have many design tools. We have a lot of material. At that time, when they built these complex timber structures, they had mainly linear elements, so like beams. They were not big panels and so on. Now we have a big choice of panel plate solutions like CLT or big dimension LVL and so on. We have even systems that have been developed. So there's a huge choice on like a smorgasbord in being able to select many solutions. And of course we have a lot of tools, CAD/CAM. We can digitalize our projects. So I think this will give again many new potential to the engineers and architects. So these kind of regular structures are quite easily be done by many people. Let's have a look at 2 very special structure. One structure relies on, so they're both multiply curved structures. The first one I'm going to show you is relying on really high quality, high tech beam material that is used. So you're using really the best material which is available. And you figure out the way of erecting these structures. You will see afterwards that these structures can be erected by skilled carpenters. You don't need any specific tools. The trick is rather in trying to develop the solutions in a way that everything fits together nicely and that the geometry is very well defined when you build these things. So this is one of the solutions which is still fairly easy. This is also a Shigeru building. It's in Metz, Centre Pompidou. What you have in here is 4 layers of beams, 2 layers running always in one direction, and you kind of stack the layers together, which simplifies very much the connections. You can think about what members are continuous and where you splice it and things like this. Whereas if you look at the timber member themselves, still very complex. You cannot get this kind of shape in one go. So you have to have this doubly curved thing. You have to first build a glulam beam in order to get the height. Then you have to cut it up again in order to bend it in the other direction. And maybe you will still have even to grout a lot of the material away in order to get the final shape. So this is maybe not very reasonable. There's a lot of waste in that and a lot of process. But the solution, of course, is fine. As you can see here, all the connections, again, everything is prepared using CNC technology. Now, the latest, one of the latest things that is being built now is this Swatch building. Hayek has a lot of money, and he has taken on board Shigeru Ban, who came up with the design. This is a snake or a reptile. Here you would have a 5-story timber building, and so this snake bites into that. This is about 100 and something meter long, and across it's something like 25 meters. There is a system behind that, apparently. I think every one of the mesh is not larger than 2.3 times 2.3 meters, but all of different geometry. The whole structure is composed by something like 2,500 different elements, and not one is the same as the other one. So you have to digitalize every single member and to process it individually and bring it to site and erect it. The company, Blumer Lehmann, who did all this work, especially the final shaping of the members, they could do something like 28 members a week, not more. And everything was then brought onto site just in time. As I learned, they had something like 8 to 10 members, which they had to do again because they wouldn't fit. On site, you have no chance to do any corrections. Either it fits or it doesn't. So this is under construction. Here again, one of the rules is cover your structure, and this is very critical. If you have some geometry changes due to shrinking and swelling, you will not be able to fit in the new elements which you bring in afterwards. Here you can see a closer look. So looking at these ribs, they're all twisted, they're bent, most of them doubly curved. And what you can see also that many of these members work on a principle of a lap joint, half lap joint. So you have a continuous part on the bottom, a continuous part from the other direction on top, and you stack one on top of the other. You can see that a little bit here. So the member here is missing, is going over these three spans here. Here are the connections in order to take away your shear. And then you have these half lap joints that allow you actually to build up this structure. So probably not very economic. For this span, this beam height is quite big, but this is one possible way of looking at such structures. You can see here a closer look. If you look at these fellows, I think you cannot have more than 3 connecting points. Otherwise, there is no way to fit in from a geometry way the pieces of timber together. And these members here, you see, they go all over the place. This one here, so everything must be erected. Quite interesting. All very precise. Every member has this final shape, and it fits. You can't do anything on site, and so. Because it fits that well, tolerance is basically 0. Across the span, 25 meters, no deviation from the planned geometry, and longitudinally on 50 meters, they had 2 or 3 millimeters. But this is logical because everything goes together like pieces of Lego or something like that, and it must just fit. But you can imagine that the work needed to program every single member here to be fabricated and brought on site. This is the structure before it's clad. Very precise, so even the people looking at the cladding, they were struggling. It was so precise, they had to be very precise as well. So the cover of that structure is like a scale type cover. It should look like a reptile in the end. So this is one possibility. Another very, very interesting possibility is trying to get some load sharing in using average or lower quality timber, but just using heaps of it. This is quite interesting to use short members, very simple geometry, and try to get a complex geometry in a different way. Let's have a look at this structure here. This is the robotic development center at ETH in Zurich, and there's the roof. It's not looking spectacular at all, but it's basically you have these hills, and underneath there are some trusses which form this roof You can see here the truss that is actually fabricated. So this truss consists of heaps and heaps of small, short, maybe maximum 2.5 meter long standard board sizes of a standard quality. So what this fellow does here, this is a robot. He gets from the timber stack, he gets the board, he brings it to the cutting station, and then he actually places these pieces at the correct position onto this truss. So it's all by stacking. This is fairly easy to be done. So Grammatio Kohler, the people who have developed the routines for that, they're used in building brick walls which are doubly curved with very precise positioning. So that was applied here in the first time in one of the first times for this timber structure. As you can see here, in the previous example, the geometry is given by the location of the joints, and the joints fit together. And there's just one way to put it in. But this, where do you put this bar, which is just slightly tilted, moved longitudinally? So the robot has to have all this information, and then he needs also the information. What this robot does, also he does the connection. You can imagine the work needed in order to design this connection and give the commands or the task to the robot to put these nails at the right place so that they don't overlap with the nails underneath and so on. But very simple, and this structure works. You could imagine it's like your gang nail trusses you have, where you just put them very closely together in order to have a bigger strength in a package of trusses. In terms of robustness, this is very interesting. If, say, this fellow here breaks, not too much of a problem. What we did, of course, is at our school, we would test some of the critical trusses for strength and stiffness and trying to find out where the weak points were. So this was quite, it was very successful, actually. One could identify also where the problems were. After that, it's just a matter of doing the whole process and producing these trusses. I forgot one thing. In order to get this geometry, of course, you have always to check if you're on plan, actually. So the robot does also the measurements in order to make sure that the final size of your truss is correct. And the future routines will also, of course, integrate the loops that if you're out of plan, you give new order to the robot to correct that in order to be in plan as well. It's a little bit like free cantilever concrete structures where you always do this check. Quite interesting. And then, as you can see here, this is one of our leading carpenter enterprises. They build all these structures. So in order to do these fellows here, there's just one person standing at the control center to check if everything is going all right. There's not one single person who has done one single operation on that structure, all by robot. And then you bring them in and then have your roof structure, which is very interesting, exciting, very light. You have the truss situation to bring all the services in, and you have quite a pleasant look from the inside. So this is a completely different approach, very, very interesting. What we have been looking at was basically this system here in layering and having continuity was the Shigeru-bound first thing. This one here are like the older structures where you have the node, where you can vary the geometry. Stacking, all this and this are all stacking, which is fairly easily. You can have that flat or 2D or 3D. And we were looking together with Grammatio Kohler in going into space. Can we also do 3D spatial free shape structures in using short members to do that? So this was a big research program where we were working a couple of years on that. Here again, the robot knows where this member goes. So there's nothing defined. The final position is not given by any cutting in the timber or whatever. You have to do that by the robot. So the to be able to build this kind of thing were developed, and we were also looking at the connections, how to build these connections. So what the robot does is he takes the piece of timber, he brings it to the cutting station where the final cutting is done. Then you have to check if the piece is in the right position, or otherwise you bring the correction, you bring it on site, and this was the only manual at that stage operation we did in order to have just a screwed connection. But we have done some further developments in trying to use glued or adhesives for solving this connection. You know that face gluing is very easy. End of grain gluing is virtually impossible. We were thinking maybe we could still find solution. We were looking at solutions where we would treat the surface in order to get a kind of depth, either with drilling or here in pinning a sharp metal point on it to have a bigger surface. We would use very high viscous adhesives, which would go really to the end of these grooves, and these adhesives they cure within 2-3 seconds. So basically, if you pour the adhesive, when you have finished pouring, it's already taken. That's one of the tricks. So inject it under pressure, and we were working around that, looking at the possibilities like end grain here, side grain here, with or without treatment, and also looking at some backup solutions, doing the tests accordingly in order to get some figures so that the engineer would be able to calculate something. And this structure here was actually built by the robot, knowing exactly where to place what timber members. So here again, the principle of having no wasting, now working on complex shapes, just using very average quality timber. What you need, of course, is everything must be planned, everything must be digitalized. So you have been talking about Grasshopper, and other tools. So there's an interlinkage and data transfer from one program to the other to make sure in the end that the robot knows where to put the exactly cut piece to the right position. So what they did here is just an exhibition piece. This fellow stands on a turntable. The robot is sitting at one side, and it turns around, and the robot, this was the maximum kind of size that the robot could do in putting in all the connections. Very interesting stuff, and I think so this actually goes away from simple stacking into real 3D applications. The next trends now are not looking only at having free shapes using linear member type of solutions, but looking also at using like panels, like CLT panels. This is a theater in Vidi in Lausanne that has been developed at the University of Technology in Lausanne, together again with some leading companies in Switzerland. There are some freaky guys who can actually design the routines in order to be able to feed in all these members in order to get these quite complex 3D shaped origami type solutions. So very interesting stuff going on here. We are currently looking at programs. We have also a couple of robots at our school. The next step will be to have interaction between the different robots, to talk to each other, to pass one member to the other, or one robot does one task, the other does the connection, for instance. There's still quite a lot of struggling with this kind of technologies, but I'm pretty confident that we will get some interesting solutions. And as I said, many of the companies, robots have been used in manufacturing furniture, for instance, already for a long time. And now the robots are getting into the heavier industry where they fulfill tasks that cannot be carried out by human, or where the human could be used for some more intelligent kind of work to be done. So the question, of course, is what is the usage of all that? Why do this? This is where we come from initially. That is state of the art now. We have to start to think with many trades, with steel people, with concrete people, with architects, with building physics, and so on. And I think in future this task is going to be more and more difficult. And I think one of the keys is maybe BIM, Industry 0.4, in order to get really to the to handle that, because I think complex structures in doing all the design right and everything is already quite a big task. But looking at other interactions, it gets really complex. I think this kind of buildings, that they are worthwhile doing it because it's like a playground for architects and engineers and technicians and developments. All the technology you can develop here, you can of course use also for some simpler tasks, and this is basically the goal of it, and I think it's really worthwhile doing it. But I think we struggle for the moment still with some interactions with the programs. You have a model somewhere, you export it, and you cannot import back and stuff like that. But maybe one of my follower speakers will have some more inputs on this side here.